So the following question is this collision elastic or inelastic? So is this collision that we've got elastic or inelastic? So I've just drawn out the collisions again. And I've written the statement, if it's elastic, that means that the kinetic energy is conserved, total kinetic energy before equals total kinetic energy after. Inelastic, the total kinetic energy before is greater than the total kinetic energy after. Now, notice on this diagram here, I have not split into x and y's. So there, I've not put the x components and the y components. Energy is not a vector, so we must use scalar values. So here we have got the overall speed of 2 meters per second, overall speed of 3.45, which we calculated. We found this angle of 17, we found this angle of 30. We know that this puck originally was not moving, and this puck was moving to the right with 5 meters per second. So we do not look at dimensions when we are looking at conservation of kinetic energy and whether it's elastic or inelastic. So let's work out the total kinetic energy before. So let's have a look at the total kinetic energy before. Total kinetic energy before is the kinetic energy of puck A plus the kinetic energy of puck B. Puck A plus puck B. And that's a half mv squared, half times 0.1 times 5 squared, plus 0, because this is not moving, no kinetic energy. We get a kinetic energy of 1.25 joules. Kinetic energy of 2 pucks after, that's a half times the mass times by the speed of A squared, plus a half times the mass times by the speed of B squared. Do not bring these two speeds together as 5.45 meters per second and then square it. It's not going to give you the same answer. Okay, get the kinetic energies separately. And we get a total kinetic energy afterwards as being 0.8 joules. Clearly, we see that the kinetic energy before is greater than the kinetic energy after. Therefore, the collision is inelastic. Okay, so there's another way for your syllabus to determine whether a collision is elastic or inelastic. So what I'm doing is I'm drawing the same picture out, but no values apart from this puck equaling 0 speed. Now, when this condition is set, where one of the object is not moving, the other is moving to the right, and then after the collision, object A moves off at angle theta 1, object B moves at angle theta 2 with their respective speeds. This is your core prac as well. So this entire example that I'm going over is essentially what you are going to do with a set of marbles, and you are going to see whether the collisions are elastic or inelastic and whether momentum has been conserved or not, and you verify both of those statements. So there's another way of looking at collisions of whether they're elastic or inelastic, and specifically for this example. If these two angles add up to 90 degrees, the collision is elastic. That's something that your examiner wants you to know. If these two angles are less than 90 degrees, then the collision is inelastic. Okay? Or if it's greater than 90 degrees as well, the collision is inelastic. Now, there is a proof that your examiner wants you to know, but I've added a lot of detail in. You don't need to add the same amount of detail here. Now, all of these masses are the same mass. Okay, so they are exactly the same mass. So what I've done is using the idea of kinetic energy is being conserved and the momentum is being conserved, we can arrive at this angle here equaling 90 degrees. So what does your examiner want you to do? So recognize first, momentum is a vector, velocity is a vector. Okay, so in the first, the momentum of object A, remember there's no momentum of object B, so I've not shown that here because it's 0. So the momentum of object A equals the momentum of object A afterwards plus the momentum of object B afterwards. And in terms of vectors, what we can see is that mass times velocity, velocity is a vector, and the masses cancel because they're all the same mass on both sides of the expression. And what we've got here is that the velocity vector of object A before the collision is in this direction. Why? Because the object is moving to the right. The velocity vector for object B, object A, after the collision is off in this direction here. So which is why the arrow is pointing that way, and that, remember, the angle is θ1, and object B is moving off in this direction with an angle of θ2. So there we go here. And we know that in terms of vectors, the sum of the vectors afterwards should equal to the sum of the vectors before. So if when we draw this out, the vector, velocity vector before is equal to the sum of the velocity vectors of A and B afterwards. I've put the respective angles in. So if this angle here, we could take a θ1, and this angle here, we know, is θ2, and alternating angles, that makes this θ2 as well. So if we've got as a elastic collision, this angle here should equal 90 degrees. Right now, we're not sure of whether it does. So these vectors show the vector triangle. However, there's nothing here to suggest that this angle is 90 degrees yet. But if we want to know what the length of this here is, we will take the magnitude of vector A, of velocity of A after the collision. If we want to know the length of this vector, we will take the magnitude of object B after the collision. And if we wanted to know the length of this vector, we would take the magnitude of the velocity of object A before the collision. And I've written that here. So that's the length of that vector, that's the length of this vector, and that's the length of this vector. So I've just put those next to each. The directions are directly related to the directions of the vectors. So these directions are the same. So what we've got here is essentially a triangle. And if this angle is 90 degrees, then Pythagoras must apply. So the square of this velocity plus the square of this velocity, the square of this velocity, the hypotenuse, is equal to the sum of the squares of the other two sides. So we got the idea there. Okay, now we know the momentum is conserved, but right now we are not sure whether it's elastic or inelastic. For the condition for elastic, we know that the kinetic energy before and after must equal the same. And considering they're all the same mass, that's the kinetic energy of object A before the collision, object A after collision, object B after the collision. And what we see here, remember when we said that we're not looking at X and Y components, we're just looking at the magnitude of the velocity, the overall velocity. And now I've written it in with the magnitude signs. Before I didn't. Now we notice that the halves cancel on both sides, the m's cancel, and what we're left with is that the velocity before the collision squared equals the velocity of A after the collision squared plus the velocity of B after the collision squared. Now that is Pythagoras. And what we said was if A is equal to 90, then what we have is the square of the velocities afterwards should equal to the square of the velocities before. And we have just shown that. Okay. So that means this angle, so Pythagoras does apply for the magnitude of velocities before and after. And that means this angle is equal to 90 degrees. And if this angle is equal to 90 degrees, then these two angles are also equal to, so the sum of these two angles are also equal to 90 degrees. Now what I would like you to do is answer this question here. So I'm scrolling down. So this question here. So you've got a truck moving to the right along a road, a car moving up the road, so the angle between them is 90 degrees. You can consider this as X and this as Y. What happens is they are colliding with each other. The truck has a mass of 20,000 kilograms. It's moving at 15 meters per second. The car has a mass of 2,000 kilograms and driving at 50 meters per second, and they collide at the junction and they get mangled between each other. So they join as one. So after the collision, it becomes one object. So they're stuck together. What we want to know is which direction does the mangled wreckage move afterwards? So which direction? So we know that generally if two things collide, they will move off at some direction. This way, we want to know which direction does the mangled wreckage move afterwards. Now, if you consider a bearing, you can give me the answer as a bearing, or you can give me the answer relative to the horizontal, the angle relative to the horizontal. Okay, so we are looking at conservation of momentum. Separate X and Y, and then let me know your answer, and then I'll go over it in the next lesson.